Thank you very much for this nice introduction. And first of all, I have to thank the organizer of this event to give me the opportunity to talk about 25 years collaboration with Akira. So this collaboration was very, very fruitful for us. And I know Akira more than 25 years. When Akira came for the first time to our institute, I was a very young postdoc. Also 1 year after my postdoc examination. And Akira follows an invitation of Eberhard Jeschke. So Eberhard Jeschke was the leader of the accelerator at this time. And this photo shows Akira and I in '87 during his first stay. And at this time, Akira was employed at the Institute for Nuclear Study in Tokyo. Also not INF. INF came later. So at these 2 months when Akira was staying in our institute, we were working on RF sticking and multi-turn injection. So RF sticking is a procedure to fill in storage ring with particles. And this is an extraction of an internal report which we brought together. This is the first report from us. And 1 year later, the TSR, the construction of the TSR could be finished. So this is the TSR storage ring, and the TSR storage ring has 4 straight sections. One straight section is for electron cooling, one for experiments. This straight section is for RF system and diagnostic, and this straight section is for injection. And in the commissioning phase, Akira came to our institute again. Normally Akira is in our institute every year. And he helps us very much in the construction phase of the TSR. And the main research field of our storage ring is atomic molecular and accelerator physics experiment. And the subject of our early collaboration was also the injection, extraction, and beam cooling at the TSR. So at the beginning of the TSR, we are using RF sticking to fill the TSR with particles. So this is the first publication of us. This is Giovanni Bisoffi, who sent greetings also to Akira to this event. And with RF sticking, we could increase the intensity from the injector. We could increase the intensity from the injector by factor 700. And with this injection scheme, the momentum spread was very huge, about 3%. And this corresponds to a beam temperature of 30 million degrees. And 30 million degrees is the double of the temperature which is inside the sun. Also, with 30 million degrees, nobody can make experiment. It's too hot. And therefore, we have to cool the beam. And cooling is very simple. So here, we have an electron gun producing electron beam. And this electron beam is much, much colder than the stored ion beam here. The electrons are guided to this cooling solenoid. And here, heat is transferred from the ions to the electron beam. The electrons are always renewed. And therefore, the ion beams can be cooled down. And with electron cooling, very small beam sizes, transverse beam sizes, could be reached. And the diameter is determined by the intensity here. And electron cooling can also be used for injection. Also, when we call this injection scheme electron cooling stacking, and this injection scheme was developed together with Akira. So in this injection scheme, we fill the transverse phase space with particles, and electron cooling compress this phase space. And then here we have new phase space available for new multi-turn injection. The beam is injected again, cooled, and so on. And with this injection scheme, we can increase the intensity of the stored ion beam by a factor 4,000. And the time to inject the beam is about 1,000 seconds. And this advanced stacking method was then published in 1990 at the 19th International INS Symposium on Cooler rings and their application in Tokyo, 1990. And this INS Symposium was organized by Takashi Katayama and Akira Noda. And this is the publication for this symposium. And here we see a picture of the participant of this workshop. So here's Akira, here am I, and this is Eberhard Jeschke. Eberhard Jeschke has invited Akira for the first time to come to our institute. And he left the institute end of December 1990 and to be a director at BC. And exactly at the same day, Akira got a full professor position at INS. Yeah. And in the early years of the collaboration between ECR and MPI-K, we were mainly working on a slow extraction system of the TSR. And these two pictures are taken in this time period. Also, the first picture shows Toshiyuki Shirai. Also, Toshiyuki was a master's student and a PhD student at ICR and an assistant professor until March 2008. And the results of RF staking are published at the EPAC 96 conference in Sitges, Spain. Also here is Akira, and here his wife, Kaiko. Yeah. And also some colleagues from Max-Planck Institute are shown here. Also this is Roland Rebno with his wife and son, and this is Robert van Haan. And here is also Eberhard Jeschke. And collaboration between ICR and MPI-K was much more intensive after signing the Memorandum for Scientific Cooperation between ECR and MPI-K. So this memorandum was signed by the former director of ECR, Professor Shinyo, and Professor Dirk Schwalme. He was a director in our institute. And this memorandum for scientific cooperation regulates the promotion of scientific cooperation, the exchange of scientific information, and the promotion of joint research projects and supports of contact. And here is written, the memorandum automatically extended until it's suspended by the signatories, but both are retired, and this means this memorandum is infinity. This cannot end. So, and this picture was taken during the draw-up of this memorandum of the scientific cooperation. So always, when I hear in Kyoto, a picture is done in front of the cyclotron magnet. So here is Akira, and here is Giovanni Bisoffi. He sent some greetings. And here am I, and here Toshiyuki Shirai. So, no, I have about maybe 10 of these pictures. So, and an example, also we had a lot of activity here. And an example of a joint research project was electron cooling of a longitudinal hot ion beam. So, if the momentum spread of the ion beam is very large, the cooling time is very large due to the small cooling forces at large velocity deviation. And to decrease the cooling time, the whole velocity spread of the stored ion beam can be accelerated with the help of induction accelerator to the stable point of the electron cooling force. Also with this method, the cooling time could be decreased by a factor 4. And this picture was taken during such an experiment at the TSA Heidelberg. Also here is Toshiyuki and here is Hisham Fadil. Also Hisham Fadil was a master's student and a PhD student at ICR, and after finishing his PhD, he came to our institute to be a postdoc, and he had this position for 2 years. And we got really a lot of help from Hisham in the construction of our new storage ring. And Toshiyuki, I believe almost everybody knows him, and so I need not to introduce him. And his longest stay period at our institute was about 5 weeks in 2000. And at this time, we were mainly working on investigation of electron cooling. So we measured cooling forces and compared this measurement with calculation. And so then we wrote a report, and this report had 36 pages. So this is the introduction of this report, and this report was then published in 2001 at the Kyoto workshop on ion beam cooling. Yeah. So this is the report, is inside this book. And this is so from each storage ring, people were sent to this workshop to discuss the possibility to realize crystal ion beam in a storage ring. In a crystal ion beam is a beam which has a very small temperature, longitudinal and transverse. And at this workshop, also Akira and Toshiyuki introduced the LSA storage ring, and this storage ring fulfills almost all requirements to make a crystal in a storage ring. And after this workshop, this was end of November 2001, the construction of LSR storage ring starts. And in 2005, the LSR storage ring at ICR was completed. So this is a photograph of the ICR, and this is much, much more compact, this storage ring, than the TSR storage ring in Heidelberg. And the main research field is beam physics of ultra-cold ion beams. And the lattice of this storage ring is really unique to fulfill all requirements to make a crystal in a storage ring. There is no other storage ring available which fulfills this requirement. And for example, this storage ring has special deflectors to avoid the shear movement which can melt the crystal ion beam. So this special deflector consists of magnets and electrostatic fields. So this is the cooler of LSR ring, and compare to the cooler in Heidelberg, this cooler is much, much more compact. So this is the smallest working electron cooler in the world. And CERN will build a copy of this cooler. So CERN is the leading, is one of the leading accelerator facility of the world. So where the LHC is located. And CERN now will build a copy, exactly a copy of this cooler, because this cooler is very, very compact. And the first results of electron cooling was then discussed in 2007 at the ion beam cooling workshop at ICR. So here is Akira, and here he gives some overview of what our LSR project. And one of the most exciting talk was the talk of Toshiyuki. Here he talked about the realization of one 1D ordering at the LSR storage ring. So this shows the experimental results of one-dimensional ordering. So here the Schottky power is shown. So the Schottky power is increasing with number of particles, and when the number of particles reach about 2000, the Schottky power decreases. And this is a sign of one-dimensional ordering, where the protons has a constant distance of 1 centimeter to each other. Because this distance is fixed, all protons are moving with the same velocity. This means the momentum spread is very, very small and this is recognizable at this transition point, where the momentum spread was decreased to about 10 to minus 6. And this momentum spread belongs to a longitudinal temperature of 0.3 Kelvin. Maybe at the beginning of the talk, I was talking of ion beams having temperature of 30 million degrees, and now we have temperature of 0.3 Kelvin. So these beams are very, very different. So, and this result was then published in peer physical review letter. And also we are very happy to be a co-author of this publication. And much higher cooling forces can be achieved with laser cooling. So laser cooling can be described with absorption and emission of photons, where in the average the ions get the momentum of the photon. And with this laser cooling, much stronger longitudinal cooling forces can be achieved, but there's only one longitudinal force, and only indirect and transverse cooling can be reached. And at the LSR storage ring, transverse cooling is done by coupling the horizontal and vertical synchrotron motion. So this picture shows the coupling of the horizontal and longitudinal motion. So if the synchrotron tune is set to a value of 0.07, where this relation is fulfilled, the horizontal beam size decreases to a very small value. And this beam size corresponds to a temperature of 200 Kelvin. And the longitudinal temperature is increased here. And this was published last year by Nakora et al. And this transverse temperature is too high to produce a crystal. And to produce a crystal, this temperature has to reduce maybe to 1 Kelvin. And this temperature can be reduced by reduction of the particle number, which is shown here. Also reducing the particle number to 10,000 reduce the transverse temperature to 20 Kelvin. And yeah, these results was published at the beginning of this year by Soda et al. And this is a comparison between the achieved beam temperature in different storage rings. Also, this temperature is the record. And yesterday there was another experiment. In this experiment, these two temperatures could be reduced below 5 Kelvin. So these 5 Kelvin are the lowest temperature, transverse temperature, which are produced with laser cooling. And these temperatures are very close to the temperature which is estimated to get in crystal string. So this is about only factor 5 different. And I'm sure also this string can be reached in the LSR storage ring and in no other storage ring. And the approach to realize an ultra-cold ion beam temperature we have summarized in one chapter in a Springer book, Atomic Processes in Basic and Applied Physics. And this book was published 2012. And so now I come to the end of my talk, and I have to say really, the 25 years of the collaboration with Akira was very fruitful for us and especially for me. I learned a lot of things from Akira, and I hope that the collaboration can be continued also after his retirement. And thank you for your attention.